use this. Sorry? It looks like it's on. And the sound responds. Yeah. Today I will not insult President Trump, so. Okay. Um, oh, it's still before 9. Surely will not start before. Oh, really? Okay, great. Okay. Good. Then Okay, good morning. So, uh, yesterday was largely a historical overview of where entropy comes from, uh, how it emerged in thermodynamics in a somewhat mysterious way, and how subsequently, towards the end of the 19th century, a more microscopic picture of entropy was developed. Uh, that allowed you to, well, initially first have a different understanding, and afterwards also it allowed you to compute uh, the statistical mechanical properties of systems. So basically that is what Gibbs did in his famous 1902 book. Um, the reason why I devote so much attention to entropy is that if you look at transport processes, the first way to describe transport processes for systems not very far from equilibrium is to look at what's called irreversible thermodynamics. The thermodynamics of systems that are out of equilibrium, but not very far from equilibrium. And I should be a bit careful about specifying what I mean by that, because it can be that a system on the whole is behaving in a wildly non-equilibrium way, but still locally the things are not very far from equilibrium. So one of the crucial assumptions that will come, we will encounter when talking about non-equilibrium thermodynamics is the assumption that you have local thermodynamic equilibrium. That means that locally the properties of the system are described by the same thermodynamic variables that you would use to describe a system in equilibrium. The difference being that whereas in a system in equilibrium, like the pressure or the temperature or the chemical potential is constant throughout the system, here in non-equilibrium thermodynamics, these quantities will be varying in space and possibly even in time, but let's say initially just in space. And this will create fluxes in the system. Particle fluxes, it may be electrical currents, it may be even flows. Which is very important for reasons. And so we want to see how this comes out initially out of the non-equilibrium thermodynamics, and then later, and that's probably going to be tomorrow or possibly early next week, we'll look at the situation where you look at how these same phenomena can be described at a purely microscopic level. So if you do numerical simulations, how you can compute these transport phenomena directly from the dynamics of the particles that play a role in the system. Now, I will. Why is it doing this? That's right. Let me first maybe temporarily lower the screen to see if it. No, what I wanted to do is to just show a few slides, but I find it useful to have a presenter view, because then I know what I'm going to say next, and that's and I was not giving me that, so that's why I was a bit concerned. But let's see, it should be coming. No, it doesn't give me a presenter view today. Okay, so it's fine. So this is where we stopped yesterday, and no, this is where it even stops today. That's interesting. Um, Usually the trick is then to take it out and to put it back in. What does it say? Nothing at all. It is HDMI, yes. Um, it is actually not so important, um, because the things I just raise the screen again and just continue on the blackboard. So this, yeah, you just take it up, and I because before I, so the last thing I was discussing yesterday is actually still on the blackboard, so that's actually good. Uh, and in my typically brilliant way of organizing the blackboard, it somehow ended up here in the middle. And basically what I was saying is that if you look at the statement, heat never flows from uh, cold to hot, then you first have to ask yourself how much heat and what do you mean by never. And the thing is that if you take an amount of energy of the order of the thermal energy, then the probability that it will flow from cold to hot, if say you have a few degrees temperature difference, is very, very large, like almost 50%. If on the other hand you take an energy packet, so you really start transferring a kind of heat that you can almost measure, but not quite, something of the other, I gave you an example of 10 minus 12 joule, then the probability that that amount would flow spontaneously from cold to hot became utterly negligible. The probability of that going from cold to hot rather than from hot to cold had a probability ratio of the order of 10 to 10. Where was it? 10 to the power 10 to 6. So or even sorry, then actually the ratio was 10 to the power 10 to the e to the power 10 to the 12. So it basically happens. Well, as I said yesterday, if you're a physicist, you say it happens never. If you're a mathematician, you say there is an epsilon probability that will happen, but that epsilon is so small that usually you don't worry too much. I still have to go back to the one case where you say, yeah, but I mean, let's look at things of order kT flowing from cold to hot. I mean, can we never say anything about that? Because that seems to be about as likely to go one way as the other. And that statement looks correct, but it's not completely true, because let me now just erase the surroundings to make it a bit cleaner. The thing is that this was the probability that an amount of energy of the order of the thermal energy would go from a system at temperature T2 to T1, or the other way around. I'll have to figure that out. The main thing is that if T1 and T2 are not too different, you get here something that is much less than 1, and so the ratio of the probability is close to 1. You say, oh, so heat can flow from cold to hot. Well, yes, but if you do the experiment many times to get statistics, then the probability that this will happen n times is this to the power n. And then you can see that even if this number initially, for instance, this ratio is only 0.99 or something like that, if n is larger than 100, you're already down to 1 over e, and if n becomes a million, then it basically just it goes to 0. So the basic it means is, if you look at the probability that after a million experiments the average has gone from cold to hot, then still you'll conclude that it hasn't happened. So on average these experiments give you exactly the same as when you try to all at once transport one chunk. Okay, that's just how you should read this bit of the second law. Now, the other thing I wanted to say is it is a bit of a detour, but hopefully I'll be able to get back to it later, is that I'll start erasing more things. I'll erase the wonderful heat engines. Um, it's the following that um, I I mentioned that we have the famous Boltzmann or Boltzmann-esque hypothesis that S is k log omega or W, whatever you want, where this is the number of states of the system, and this in order to use this expression, you have to assume that all states of a system are equally likely to be occupied. And in the context of classical mechanics, that's a very reasonable statement. So if I schematically draw here phase space, I mean my 6 n-dimensional drawing skills are limited, so I do it like this. And I divide phase space up into volume elements that actually, so this is P, and so that's like a lowercase p, and this is Q, so you have here volume elements that in the end, to make it consistent with quantum statistical mechanics, all have a volume h per pq pair, so h to the power 3n in a 3-dimensional system of n particles. Then, because of the dynamics of the system, as every volume element is occupied, I cannot intersect, so at some point I basically run out of drawing skills, but as every volume element is visited with equal probability, it is indeed reasonable on the basis of classical dynamics, classical mechanics, to assume that all states are equally populated, and then and when people transferred from classical mechanics to quantum mechanics, they more or less, without much additional reasoning, said actually we interpret these things as quantum states, although they may be not at all, they're not in a phase space, so you can then remove these coordinates. But we just look at different quantum states, and we again assume that there's an underlying dynamics of the system that will ensure that all quantum states with the same energy, same volume, the same number of particles are visited with an equal probability. Now, there may be other systems, non-equilibrium systems, where you prepare states with a protocol that is different. And so in this context, I think, for instance, of granular materials. Granular materials have also states, packings. So you can generate different packings in a granular material. The probability of visiting different packings, in principle, can be very different from can be different for different packings. In fact, I'll discuss next week that Sam Edwards postulated that if you prepare a granular medium, or what he called at that time a powder, that all packings are equally likely. But that's a courageous guess. I mean, it's a hypothesis at that stage, and so in general you have to consider the possibility that not all the states are not all equally populated. Is that serious? I mean, does that affect your ability to then construct from the whole framework something that looks like, well, a thermodynamic entropy that with which you can continue? And the answer, at least my answer, but you may disagree, is that actually it still allows you to get an entropy that is fine. In the end, what I'll end up with is what's typically called Gibbs entropy, but I should stress the Gibbs entropy is always derived for a system at constant temperature. And then you say, well, and the states with a high energy are less likely to populate than states with low energy, and then you get an entropy that looks different from this one, but that's for an obvious reason, because different energies are not assumed to be equally likely to be populated. But even if you have a system where all states have the same energy, it could be that, for instance, this state is very likely to be populated, this state a lot less, this state hardly at all, and so you can imagine that the different states have all their own probability of being occupied. And now comes the thing I said at the beginning. Oh, I forgot. I should always have this curve at the beginning, describing my understanding of science. So here is understanding, as you know, here's time. This is when I started my undergraduate studies. This is how I progressed, and this is where I'm now. And so the thing is that it is not. I mean, to me, it becomes not obvious except in the context of classical mechanics, that you can simply say that counting states is the best way, or is the obvious way to say how likely a system is in different states. So we typically we say, oh, if I have a system 1 with omega 1 E1 and another system 2 omega 2 with E minus E1, so total energy is fixed, and I move a bit of the energy from here to there, so I get here omega 1 E1 plus delta E, and here I'll add omega 2 E minus E1 minus delta E. Then I just look at the total number of states and I say, well, for instance, if the total number of states has gone up, this product is larger than that product, then that state's more likely. It sounds extremely plausible, but is that really so blindingly obvious in cases where you don't have classical mechanics to back you up? So this is why one of the things that I find difficult. But anyway, if you really assume that counting states is the way to estimate the probability, then and you now have systems that can be in different states with unequal probability, then we have to see what is the average number of states of a system. And in this case, what you really have to do, at least what I find I have to do, is to introduce the concept of an ensemble, which usually in statistical mechanics is introduced at a stage where you don't need it at all. Yesterday I didn't mention the word ensemble because I didn't need it. Today I actually do need it, and this is also, I guess, why Gibbs introduced the ensembles, because he needed it fairly early on. So basically, if I have a system and I just make copies of the same system, and total number of copies of the system is m, and m is incredibly large. So I mean then you can say, so if the total number of the probability of finding a system in a particular set of states is determined by effectively the number of realizations, then what you do is you say, well, I look at the total number of realizations of this combined system, and then the log of that total number is equal to m, because I have n systems, times the entropy per system. That is effectively the assumption that you make. But how do we compute this number? So now we have different ways in every state. So we still assume that every system actually has this energy E. So we're not going to swap energy. We just say, well, this system could be in state I, this could be in state J, maybe state J is very probable, so this system is also in state J, and then, as you know, I can have systems in states R, Z, and 2, just for your amusement. So, and just to retrain you in my handwriting. So then you see that they could be all in different systems. So what is the average product, the average degeneracy of this entire system? So I just multiply, because we assume the systems are uncoupled. But then, of course, it depends on how I divide the how I arrange. Because, for instance, if I have a number of systems that are all in the same state, like this one is in J, this one is J, then I should realize that I have to divide all the combinatorics, because I have, in principle, m factorial ways of getting the system to occupy different states I, j, k, etc. And I have to divide by the number of systems in state I. And so in the normal Boltzmann approach, you say all the ni's are the same, but now it's not all the same. So what is the value of ni? Well, you say, well, let's look at the number, the most probable realization. So then you say m factorial divided by pi ni factorial. And now we have to take into account the fact that every state has its own probability that can be different. And now it becomes a very easy thing to compute what pi should be, because we say, well, we're going to just look at, we take the log of this thing and we maximize, so we call the log of this m factorial over pi ni factorial pi to the power ni. now it's almost n with respect to ni. For all ni, with the constraint that the sum of all the ni's must be m, because that's a Lagrange multiplier. So this is what the standard trick you always get when they do ensembles. They say you optimize with this constraint. And if you do that, then what you find basically is something that looks like log ni, and I have to make it's a minus sign, minus log ni plus log pi is a constant. That's the Lagrange multiplier bit. Okay, so there's a log ni. So that means basically that ni is pi, is pi times the constant. What is the constant? Well, if I sum over all state, the probability must add to 1 because the system must be in a state. So this sum adds to 1, this adds to m, so the constant must be m. Okay. And if you then say, okay, so now what is this factor? Because that's what we really want to know, the effective number of, the effective degeneracy of this whole big system. Well, it's then m factorial divided by, and now it becomes, and now I put in that ni is actually, well, let's leave it as it is. I'll just take the log and then do my my business. So I'll just take the log of this whole thing, log of this big omega total is equal to, well, there you get m log m. I'm blocking my own blackboard, minus sum I ni log ni, and of course the constants, the sum ni and this and the m here factor drop out. I write this bit as sum ni times log m, and then you see that what you actually get is minus sum ni log ni over m, which is nothing else than the probability of finding the system in state I. But this is m times the total entropy. So to get S, the entropy of a system, I divide by m, and then you get minus sum I pi log pi. And of course, if pi is the same for all states, that's the Boltzmann case, then pi is 1 over omega. So then this is, I take the minus sign, this becomes log omega, and sum, the pi sum to 1, and you have S is log omega, k log omega. So this one is a special case, the Boltzmann case is a special case of this one. Normally, as I said, in the Gibbs language, this is done for systems where they have all different energies, but you can see that even if you have a constraint on the energy, if for whatever reason different states don't have the same occupation, you still can define an entropy, and from that moment on, with that entropy, you can do everything you like. Now, I mean, I don't know how many of you ever wondered why phase space has to be in terms of the positions and momenta. Why not the velocities? Why not something completely different? The thing is that actually it makes no difference. You could have made your phase space, it would be not very smart, but you could have made your phase space in any other thing. The entropy would have looked like this, and the answers would have all be the same. So I mean, that's why, in a sense, statistical mechanics is more forgiving than you might have. Let's not erase this because that's really important. Good. Okay, so much about the general aspects of statistical mechanics. Let me now go back. Now, let me see now if in the meantime the screen has woken up. You never can tell. Not that I have something very important to say, but if you... I think it was not well connected there. That sometimes explains a lot. This looks a lot better indeed. This is always, oh, by the way, always the answer you get if you call a helpline. Like, is it plugged in and things like that? Yes. Okay, good. So it's usually a very sound advice. So this we know. Now we're going to talk about this. Clausius again, when heat flows from hot to cold, the entropy increases. And and until now, I was talking specifically about the case where the entropy increases because heat flows from one part of the system or from one system to another. So that's this case. This is what I was talking about all the time. Uh, but that's only part of the story, because if you now, and now I just I will not do all of thermodynamics. I will just now assume that we know thermodynamics, and we write down the expression for the variation of the internal energy of a system. I'm not sure why I'm very worried that it sometimes will switch off again. Uh, the internal energy. This is the first law of thermodynamics in terms of variation of the energy. This is the entropy bit. This is the work bit. There could be other bits that do the work. It could be electrical work. It could be pretty much anything you like. It could be a field and a dipole moment. And then there's the chemical potentials. I'll come back to that briefly, but of course the chemical potentials tell you what happens to the internal energy of a system as you move particles in or out of the system. And there's an unfortunate prehistory to the chemical potential, and that is, the concept was introduced by Gibbs in the 1870s, and Gibbs is one of those people who, or one of the very few, who never made a mistake. So actually, I had a Russian colleague. I mean, I still have the Russian colleague. He said that in the Soviet Union at the time, people also greatly admired Gibbs, and they would say that in the history of Western civilization, there are two books that are considered to be infallible. One is the Bible, and the other is the collected works of J. Willard Gibbs. But on the whole, the evidence is stronger for the collected works of J. Willard Gibbs. So, Gibbs doesn't make a mistake, except one. And actually, it's not a science mistake; it is a human mistake, because he called the chemical potential the chemical potential. And I mean, most of you are physicists. Somehow, physicists think, well, we don't have to deal with that. You do. And so this, I mean, so this is really, I think, if I say, oh, it's the Fermi energy, yeah, fine, everything is happy, everybody's happy. But if I say it's chemical potential, people immediately feel that this is slightly less relevant. So this is where I'll come back to that later on, but I just wanted to mention that. Okay, I think that I will continue now a bit on the blackboard, so I have to take off my jacket, otherwise I just can't survive. And then when I need the projector again, I now know it works, so this is fine. So you can lift it again. So we start from dE is TdS minus BdV, and again, I mean, this stands for work, although very often there may be other kinds of work, plus some mu I dNi. And that means that if you actually look not at the change in the energy, but you look at the change in the entropy, that ds is 1 over T dE plus P over T dV. Why plus? Well, actually, if you compress a system, so the volume is smaller, then the energy goes up. But if you expand the system, the entropy goes up. So this is why it's plus. And then it's, careful, minus some mu I over T dNi, where I don't have quite a simple and intuitive answer what this means, this sign, but we'll come back to that. So this is what you do, and then you say, okay, so basically this means that if I have two systems, that there's different ways in which I can change the entropy. One way is to actually transport energy, which is what I've been discussing up to this point. But I could also instead say, well, I have these two systems, and I move the boundary a bit. So I don't think of a physical boundary, because really these systems are supposed to be totally independent. They don't interact. But it means that I go from a situation where this is now V1 minus delta V, and this is V2 plus delta V. So, and then if I do this at constant energy and constant number of particles, um, then this tells me how the entropy of the whole system changes. Similarly, if I keep the volume fixed and I keep the energy fixed and I move particles from system 1 to system 2, then I get something. So let me just write down explicitly what it would mean then. So I get the general expression for the entropy change, and it is 1 over T1 minus 1 over T2 delta E. So if it's a small but finite amount, let's do it like that. Plus P1 over T1. We don't necessarily assume at the moment that anything is at the same dV. Oh, if I write, let's do D, if I do everything in D. Minus mu, well actually it's for all I, but like mu I1 over T1 minus mu I2 over T2 dNi. This is the general expression for the variation in the entropy. And so Gibbs used this expression to derive the conditions for equilibrium and but more in general for phase coexistence. If system 1 is for instance one phase like a liquid, and system 2 is a crystal, and you want to know when the two are in equilibrium, well you say, well, it means that for any small change I do by transferring either volume or energy or number of particles from one to the other, the entropy should still be at the extreme. Second law of thermodynamics. So the first conclusion is that at equilibrium, or here I write coexistence. You probably know this one. There's a banner. Oh, well, okay. Okay, so right. Plan ahead. Right. So coexistence. Good. I realize that my reading now is really getting to almost negative value. My writing is to get a negative value. Okay, so basically at coexistence, it means that T1 has to be T2. Once you do that, then it then follows that P1 has to be P2, and it means that for every species I, mu I in phase 1 must be equal to mu I in phase 2. So that is the normal condition for coexistence that actually allows us to, for instance, locate phase transitions. Because, for instance, if you compute the properties of a system numerically, this is the way you do it. You for instance, study a system by carrying out numerical simulations at a fixed temperature and pressure. You compute the chemical potential. That may be a bit of a hassle, but it can be done. And then you determine the point where all these conditions are met, and that is the point where the phases coexist. At least that's okay for first order phase transitions. Continuous phase transitions require a bit more. Now you think this is innocent enough, but actually it is not. And the thing that is not really innocent is the fact there are these constraints that you do. You write the variation in the entropy of a system in terms of, well, the variations with respect to the different variables. You write ds is, well, let's write ds dE at constant n and v. Well, I don't write explicitly all the ni, but this stands for the whole set, times dE plus ds dv, but at constant n and e, plus ds dni for all ni at constant nj. So now I really have to be n, e, and v. So I'll just indicate here, but that it's a set. Now, these things are a bit tricky because they have a constraint. For instance, here, oh sorry, this should be times dv, of course, and this should be times dni. They have a constraint because the total energy has to be constant here. So that's not in the case of changing the volume, that's not such a problem, because you have here the system, you change the volume a bit, and you say the energy has to be constant. And so it means that as I do work on it, because this is really doing work, because this was the thing had to do with the PDV work. If I do work on this system, then the total change in the energy dE is equal to Q plus W. It's the work that you do. If dE has to be 0, then and W is not equal to 0, then Q has to be not equal to 0. So this is one way of actually moving, changing the entropy of the system. You do the work, and heat has to flow out in order to keep the energy constant. And basically, because this heat is precisely equal in magnitude and opposite in sign to the work that you've done, you get this thing. But this is where the PDV has had its sign change. So that's okay. It becomes a bit more tricky if you look here, and I think because how do you transfer particles at constant energy? And now, unfortunately, I have to show if I can find my corresponding slide. One way of doing this, of actually transferring particles at constant energy, is it is actually, if you think about it, not so easy, because I mean, how do you transfer an atom or a molecule at constant energy? And so, yeah, okay, so this is the one we just had. This is the other one. So basically, if you take this literally, and later I'll argue that you don't have to worry about, but initially I would just say you do have to worry, and then I make life easier. Initially, the way you would say, oh, I mean, how can I transfer particles to a system at constant energy? And one way would be to tell the particles, well, if you come to the boundary between system 1 and 2, you just leave all your energy behind. So this is my sketch of what's happening. Here's a particle, has energy, and it says you are leaving, well, domain 1, T1, mu1, and you go to the other domain, and you have to basically drop everything you got. And then so basically what happens, you have this energy, and you say, okay, I give it away to the rest of the community, or actually if you're in debt, they have to give it to you, which you won't like. And then you come to the other side, and there you come with no energy at all, not even your own kinetic energy, nothing, and you say, can I please have my normal package of energy? And so then the others have to pay, or whatever, whichever way, whether your energy is positive or negative. And that, of course, is very strange. And the main reason why it is very strange is that the energy is not such a well-defined quantity. I mean, in relativity, yes, it is. E equals mc squared. Should we count that? Because then if I move a particle from system 1 to system 2, the amount of energy you have to leave behind is absolutely staggering. And so you can, well, it's like you talk about many MeVs in energy that you dump in the system here. And hey, wait a minute, these temperatures, in general, it is mu1 over T1 and mu2 over T2. The temperatures in general are different. And so it means that if you release a lot of energy at T1 and you get it back at temperature T2, that implies a huge entropy change. And so the entropy change that you get when you move a particle while keeping, while forcing it to not change the energy of the system, is basically undefined. And this is the thing that I wanted to show how you actually get around that, because things are not quite as bad as they seem. And so in order to make progress, I now actually have to start talking really about non-equilibrium thermodynamics and about fluxes of particles, fluxes of energy. I will not talk about fluxes of volume for a reason that I explain in a minute, and that is just because what I'll do is irreversible thermodynamics light. and there's a good reason for doing it like that, because the full version, as you can find in the Grote Mazur, is anything but light. Um, Let me phrase it slightly differently. I mean, I have the book by the Grote Mazur, which I so this is the book, the standard book on irreversible thermodynamics. Of course, the prophet was Lars Onsager. Lars Onsager takes no prisoners, so he basically assumes that if he writes one sentence, you understand all the 20 unspoken sentences and equations before it. The Grote Mazur are not like that. They usually go through things step by step. And because I have the book on my Kindle, I actually can search for words. And so I search for the word easy, many times straightforward, many times simple, quite a few. Transparent, only once. And that is basically the problem with the Grote Mazur. Because what happens is that in there, after the introduction, they have two chapters, chapter 2 and 3, where they derive the expression for the thing that turns out to be crucial, namely the entropy production. So that is not just the change in entropy of a system if you transfer particles, whatever, from one to the other. It's the rate at which it happens. So then at that point, it's like this becomes an energy flux. This becomes, well, actually this one is not is a special case, so will not. But and these become particle fluxes, and they construct the derivation in two chapters, and it is indeed you go from one equation to the next, and every equation, indeed, the steps are simple, even sort of straightforward, but they need 78 equations, and so what I would like to do before actually explaining the simple version, I will tell what the Grote Mazur do without actually doing it. And then if ever you feel the urge to read the Grote Mazur, if you have not yet done so in your free time, then at least I hope you will understand what to look for in the chapters. And so the main thing is that they look at an expression for the rate of entropy production. Now, entropy in a certain volume element can change for two reasons. One is that there's an entropy flux in or out of the system, because as you remember, entropy is a property, is a state function of the system. So the system has an entropy. I can therefore add or remove entropy to the system just by flowing it in or out. So you have the rho s. Now this is entropy density. This is that's where the density comes in. And the Grote Mazur make a big deal about whether you take the entropy per unit mass or per unit volume or per unit whatever. In the end, it makes no difference, although some things are sometimes more convenient. But I'll be intentionally sloppy about this. Then there is the divergence of the entropy current. So this is basically what flows in or out. And then what remains, this is the crucial thing. This is the entropy production. And that is the thing where actually irreversibility comes in. This is all the things that have to do with irreversible thermodynamics. But how do you get to the expression for the entropy production, the entropy flux, and how do you see what the entropy production then is? Okay, so what the Grote Mazur do, and as I said, I don't do it, is first they look at a volume element and they look at its kinetic and at its potential, they call it psi, potential energy. Now this can change, because if there are forces acting on the system or there's a pressure gradient acting on the system, pressure gradient will change the kinetic energy. If there are forces acting on the system that act against the pressure, then you have, no, sorry, that's not right. If you have forces acting on the system in general, you can change both the kinetic and the potential energy. And then you look at kinetic and potential energy together and you say, how about, well, let me forget about just, oh, I'm always at a break. Okay, never mind. So how about this? Is this of the form div j, in which case it, or minus, in which case it would be the conserved quantity. Answer is no, it is not. There's something missing. What's missing? It's the internal energy. This is what all of thermodynamics is about. So if you do things to a system, the internal energy changes, and so then you say, oh, there's something missing, because if I add to the internal energy, let's call it U now to distinguish from the kinetic energy. Then I get something else. Then you get that the total energy now really has d rho, let's call this E total, dt plus div je is 0. This is the first law in its time-dependent form. It really wants me to hold the brake. Okay, so but I started a bit later. Good. So this is the first law, but it means that you have defined effectively something that includes everything that was not included here, and you call that the heat current. So everything that is not yet in your energy current is in the heat current. Then you use the first law of thermodynamics to relate the change in the internal energy using this kind of expression to the change in entropy, the PV work, which actually partly compensates PV work done on the system as a whole, and the term things with the chemical potential. And after you've done all that, you get an expression, and I think I'll write it down just for fun, and then, but not great fun. What you get is the following. Ah, I can do it here. We all know this now. Perfect. This is a good moment to stop. So then the Rotan measure in the end conclude that the energy production looks as follows. It is JQ, the heat current, times the gradient in 1 over T. So now it is rate of change. So see, this is the 1 over T that you see here, but here it's the heat current times the gradient in 1 over T. So actually it occurs just the other way around from what you would think here. Then there is the minus sum I ji, the particle currents, times the gradients in mu I over T. And then you get terms that, and this is why I don't derive it, there are terms that come from an almost infinite number of straightforward steps that basically allow you to write then a term that goes like the pressure tensor, and actually you have to be careful. This is the pressure tensor. This is if you wish, if you take it with a minus sign, the stress. That is the result of non-equilibrium driving force in the system. So it is not the hydrostatic pressure. And so here I was always talking about hydrostatic pressure. That completely drops out of the expression. What remains is that part of the stress that is due to, for instance, shear or something like that. And this, of course, is now a tensor, and it is dotted into where this is the velocity of a fluid element. And then you have other terms, and the Rotemers you always write them explicitly, but I will not. And basically they're terms having to do with chemical reactions. So if you have chemical reactions, then they too can contribute to the entropy production. That's obvious. I mean, so if you have like, I don't know, a hydrogen peroxide molecule, which in active matter is sometimes popular, and it falls apart and it says bang, and you've produced entropy. So that's those are the things that come from the general derivation. What I will do is simply to look at these terms and show how they actually follow quite straightforwardly, and then I just hope that you believe me that if you're sufficiently patient to work through the first 2 or 3, or was like 2 or 3 first chapters that that deal with it, that you know effectively what's happening, and therefore hopefully it's easier for you to see what they're doing step by step and how in the end they end up with an expression for the entropy production. I'll continue after the break. As I said, the break is just to allow you to recover your sanity. You can look at the ceiling, etc. And then in about 5 minutes we continue. Okay, thank you. Good. So.
Hey Dan,
Yeah.
can you write down the name of the book?
Oh yeah, sure.
People are not catching the first of the 2 names.
Okay, right. Now
Or
you've
what's the name of the authors?
yes, definitely. was immediately switched to Canon. But okay, that's this is a Dover pocket, so it's not very expensive, but you can also get it online. Oh, that's well. Well, no, actually, this is you can get it online and even pay for it. Uh, but I know that in addition you can get everything online and not pay for it. But um, I I think that if we were to advertise this, then this school would be closed or something like that. Okay, so that was the word I was here. Right. Good. I think I know. If this has been there long enough, then I. Right. Good. So what I promise to do then is to give you a feeling for how you get these expressions, and actually, uh, it is easiest to actually start from what I had here. So I don't plan ahead anymore. I just take this out because there are gradients. Oh no, I should always keep this one. So I look at this and I take this bit out because, as I said, the hydrostatic pressure in this story does not play a role, because actually if you have a bulk fluid and there is a pressure gradient, the thing is accelerated. So you need obstacles to actually sort of make sure that the momentum doesn't keep on increasing. So this requires a slightly different approach. But the other fluxes are all fine. Um, so the way to do it then is to say, well, if I if I have two systems, and now I just here again always draw system and a system one and a system two, then and remember halfway through I decided to make small d's here. Then I look at fluxes of different kinds, energy, in particular energy and number of particles that can go one way or the other. But I take intentionally, I look at steady state and I look at the 1D geometry. And the advantage of looking at a 1D geometry is that the divergence of the fluxes, I mean, if the quantities are conserved, the divergence of all fluxes would be zero. So in principle, if I look at this situation, I really can look at the change in entropy due to terms like this. But now the difference is that I will say that I should have probably labeled them the other way around to make it a bit more logical. That yeah, that's right. That this is position x and this is position x plus dx. And then I look at ds, but actually I look at ds dt. And now you have to be careful. I'm now talking about really the entropy that is being generated in this system due to the fluxes, not the entropy that flows in from either side or flows out from either side, just what's being generated inside. And well, if the temperatures are very close, then I can write this as d1 over t dx times dt or dt, and then the do I say this correctly? Sorry, times dx, of course, not d. Sorry, and then I get here the change in the energy, basically the amount of energy going through this surface. But the amount of energy, and this is now the internal energy. So I mean, unfortunately I have used E for the internal energy, whereas actually in general you should distinguish between internal energy and total energy. So this is the internal energy, and the internal energy, if it flows from one system to the other, that is what we call a heat flow. So actually this is J of Q times the surface area, the cross section. So this, we assume that this, actually I should draw it now in 3D. This has a cross section area A. So this is one thing. So we get, of course this is not, I mean I should actually replace it before I do more damage to my equations. So I'll just move it out a bit, and I write that the SDT, so the change in the entropy of the system, is equal to grad 1 over T, which depends on x, times dx, because this is a position x, times the area times the heat current, J of Q. That's the first thing. And then the second thing we get here, and you see there's something, there's a minus sign, there's a grad of mu over T dx, and then again a times, and now it is for every I, so in principle again it's the sum, so sum I a, and then we get Ji, the flux of particle species I through this surface. Now the Groot Amazur make a big song and dance about the fact that the sum of if you take mass fluxes, the sum of these fluxes should add to 0, because otherwise the system is has a non-zero total momentum. It is often not quite as seriously, but you have to. There is the one thing that is true is that you have to consider these fluxes. If you have k species, there's only k minus 1 independent fluxes, no matter how you do it, and so one of them is indeed by doing it this way. Now this is nothing else than the magnitude of a volume element. So if you look at the entropy production, so we call the SDT, the amount of entropy is really product, we define it as sigma. This is the entropy, sorry, no, we don't. If we say 1 over the volume of the thing, of this the system, times the SDT, this is the entropy produced per unit volume, and that we define as sigma, and that is now equal to, and now we get grad 1 over T dot JQ minus the sum I grad mu I over T times Ji. So this is the shortened version of what I had over here. So basically I had over here, except where did I write it? Here. So you see here those two terms are what comes out of this very simple thermodynamics-like argument. This term, it is simple, straightforward, etc., and 78 steps. Okay, good. Although maybe in Callan viewer, that's I don't know. Good. So now we have to still address the issue that I said there's something strange about the energy current, because should I include the rest mass of a particle in the energy current or not? And so how can I do these things without getting into trouble? And the main thing to note is that I will just now write the shortened version here. So I say sigma is JQ grad 1 over T. And of course, if I transfer particles that contain energy, that will also be in this heat current, because part of the heat current is simply due to transfer of particles, and that is not what we normally consider the heat current, but that'll come in a minute. Minus sum I grad mu I over T Ji, the particle currents. And the trick now to make life easier is the following. You can say, well, let's look at the two things separately. There is here one part, this mu I over T can change because either the temperature changes or the chemical potential changes at constant temperature. And so you can basically say grad mu I over T is d, and actually is d mu I over T, and it's convenient to write d1 over T times grad 1 over T, and then the second term is plus grad mu I over T at constant temperature. Sorry, yeah, that is basically that's it, and plus grad mu I over T over at constant temperature. Now the thing is, if it's at constant temperature, you might as well write it as 1 over T grad mu I at constant temperature. But this one, and now I use a bit of thermodynamics, this thing is actually equal to the partial molar enthalpy, H. So you know that the total enthalpy, H, is E plus PV, can be written as sum, well, depends on how you do it, but let's write it as Ni, the number of species of type I, times the partial molar entropy. So this is basically the thing that makes up the enthalpy of the system. And this thing, the enthalpy of a particle, it contains a PV term, but it also contains the internal energy. Now this is extremely nice, because what we're going to do now is to say, well, if I've done that, I can now go back to my equation here and say, okay, we write this as JQ minus, and now note that this term was multiplied by Ji minus sum I Ji Hi, the partial molar enthalpy, times grad 1 over T. And then what remains is minus 1 over T grad mu I, again sum of course, at constant temperature times Ji. But now you see that the rest mass of the particle, all these things have disappeared, because this, if you wish, diffusive contribution to the transport of heat. So basically it's heat, that is energy that flows from A to B because particles are flowing. So it's not the flow, because the net flow we try to kill. We just want to have diffusive currents of the different species, but they carry the internal energy of the particles, and it's exactly cancelling the energy transport here in JQ. So if you look at this expression, then what you get is what is called the proper heat flow, or the measurable heat flow. It is actually a thing that is not unambiguous. But it is important because it tells you something. And I say that because if you look at the literature, I don't think that everybody has gotten that point. If you look at, for instance, thermophoresis of particles, people say, well, I mean, well, some people, I will not name them, say, well, I mean, here it's hot, there it's cold, so clearly the particles go from hot to cold, which is, I mean, based on no known physical law. I mean, but usually they think, well, because the free energy of the particle goes down. This all has to do with what the particle carries inside, and it's totally irrelevant for phoretic transport, what the particle is going on in the particle inside. Unless it influences what's going on outside, it has no effect. The particle also interacts with the surrounding fluid, so it may have some interaction potential. If the fluid is transported with the particle and nothing happens, that is part and parcel of this partial molar enthalpy. Again, it doesn't do a thing. However, and this is really where phoresis becomes interesting, if a particle moves with respect to the fluid may, in a sense, strip away a bit of the enthalpy that the particle carries. But it's only that bit that can be stripped away by the fluid. So it is nothing having to do with E equals mc squared. It's just a bit of the fluid that interacts. And then you're really back to my particle at the border. The particle is here. It moves out of the fluid with which it was interacting. It releases a certain amount of energy. Entropy goes up here. it comes there, it has to interact here at its slightly different temperature, and it takes up a certain amount of entropy. That is real entropy production. So yes, it's important, it's all in here, but anything happening inside the particle is irrelevant. And it's a useful hint if you read the literature, because not everybody gets that. Good, so this is what I wanted to say in general about uh, the, the idea of well, I mean, the expression for entropy production. I said I don't do the whole thing. What I'll do in the remaining, what is it? I forgot to start my clock, but Julien will know. You will. Well, 20 minutes. In the remaining 20 minutes, I will hopefully get to the Onsager reciprocity relations, because basically what we have done until now is to say, okay, I have a temperature gradient, and it creates a heat current. I have a chemical potential gradient, it creates a particle current. But actually, it can do more. A temperature gradient can also set up a diffusive current, like that's called the Serre effect. You have all these cross couplings, the Serre effect, the Seebeck effect, where you have one gradient, and it sets up a current in something else. That doesn't change the fact that in the end, the entropy production always couples the current to its conjugate most important variable. So in the entropy production, there is no cross coupling between J of Q and the gradient of mu over T. There's only JQ grad 1 over T, Ji grad mu I over T. Those are the things in the entropy production. But these currents can contain contribution, this contain a contribution due to this, etc., etc. So there are cross couplings in the currents, and we have to know how to deal with that. And then maybe today, and otherwise tomorrow, we get to Onsager. And so we go and erase a bit of blackboard, because the best way to discuss this, at least I find personally the easiest way, is to look at well, first at the second law of thermodynamics, and at fluctuations. And so I have a system, and where the entropy is the function of a number of variables, and it could be much more, but let me just write it like this. Well, let's do V, etc. So these are all variables that determine the entropy, and we know that in equilibrium the entropy of a closed system is maximum. So that's one thing that we have. The other thing is that we can have, if we have two systems, we can have small fluctuations around equilibrium. I said small fluctuations are quite likely, like moving energy of the order of kT from one system to the other is not an issue. So you can have small fluctuations in the number of particles, so and I could be going here, or some energy could be going there. That's a small heat current, and these small fluctuations are possible. Of course, if a certain amount of particles is transported from one system to the other, and you start it in equilibrium, then you end up with a situation that is less probable than the original one. So let's call all these quantities, just to keep the notation simple. I call this A1, A2, A3, etc. And I also, so then S is a function of this whole set AI. Maybe I should call them K to distinguish it from my particle indices. And I can expand the entropy in a power series, or at least to lowest order, in the variations of the A. So I say S for a given set A. Now what what people usually do, and I will do the same thing. All right, let's not call it I, because I'm surely I'll slip back in my notation. A plus delta AI for all the different things, and I will call this delta AI just for compactness. I call it alpha. This is alpha I is the deviation of AI from its equilibrium value. So this is the equilibrium value, and this is the deviation. So if you do that, then this is equal to S for the equilibrium values of all these quantities, plus the S dA. Well, you can say whether it's A or alpha, it makes no d alpha I times d alpha I for all the fluctuations. This must be 0 because the second law of thermodynamics says that in equilibrium we're at the maximum. So this one we can forget, the plus, and then we get 1/2 sum ij second derivative of S d alpha I d alpha j alpha I alpha j, and there we stop. So it's not that it stops there, but this is the lowest order expression that we consider. And the thing is that because entropy is maximum, this second order derivative must be less or equal than 0. So you know that as you expand around equilibrium, that the entropy goes down. And so now the other thing we have is that the entropy of a system is a measure for the probability of finding a system in a particular state. So actually we can write the probability to find to find a system in a particular state with state alpha 1, alpha 2, etc. So now it's just the fluctuations, alpha n is equal to, and I write this as e to the power minus 1/2 and then sum gij alpha I alpha j, where this gij is basically just, apart from the sign, is the second derivative matrix, which you know must be a definite negative. Now, the first thing that you can say is you can define. Remind this thing does determine how the entropy goes. So you can see how the entropy changes with a certain variation in one of the quantities, ds d alpha I, and you see that that is equal to minus sum over j g I j alpha j. So this thing, the variation of basically this tells you how the entropy changes, and the larger this derivative, the larger the restoring force, if you use the thermodynamic restoring force to try to get the system back to equilibrium. So this quantity, ds d alpha, we define as the driving force, the thermodynamic driving force conjugate to alpha. So for instance, we know already something like, for instance, in the case of the chemical potential, it would be something like mu I over T, and in the other case it would be something like 1 over T. So we have all these different driving forces that have to do with small variations in the different functions that in the different variables that can affect the entropy. Now, I'm talking about fluctuations here. I'm not talking about transport. Now comes Onsager. And Onsager made what is called the regression hypothesis. And the regression hypothesis is the following, that you say, if I have a system, and let's look first at the system in equilibrium, and this is alpha 1. I don't know what it was, the energy something. And I look at it and I find that actually it's fluctuating around 0, because by definition on average must be 0. And for instance, I have a spontaneous fluctuation and I'm here. I can see how this thing decays back to the average. Of course it fluctuates, but if I take many starting points, I can see how alpha I of t develops given that alpha I of 0 had a certain value. So I look at this situation where I look only at those things that have a certain value, alpha I at 0, and then this gives me a function that tells you how fluctuations regress to the equilibrium average. So every individual trajectory is noisy, all of them together give something that's not noisy. Onsager's assumption is that the way currents in a system under the influence of an external driving force evolve in time is exactly the same. So close to equilibrium, it makes no difference whether you perturb a system by an external force or you wait for the system to spontaneously, by a fluctuation, reach initial condition. The relaxation to equilibrium is the same. So that's a very important hypothesis, because it allows you to use statistical arguments now to see how things evolve. And so the main thing is that you have these driving forces. They are linear in the deviations, and the two lowest order. So if you have a system close to equilibrium, you expect that the resulting current, I used a, sorry, not a big, small j of some other variables L is equal to, and I have to, is proportional to the driving force, so it's linear in the driving force, and then there is a coefficient in between. And these transport coefficients tell you what's going to happen. So for instance, if you have a chemical potential gradient and this is the corresponding particle flux, then this is the mobility. But in general, for instance, if this is a temperature gradient and this is a particle flux, then it's a cross coefficient. It tells you how you get diffusion due to a particle flux. Yeah. Ah. Just because I expand. Yes, so close to equilibrium, and I assume away from critical points and things like that. So yes. Oh, so no, that's not necessary. I mean, so in this case, when I have my entropy S specified explicitly as a function of the extensive variables in the system, then I can also see how S would vary from its maximum value if I change any one of these variables, and that is the thing that you need here to define what is thermodynamic. Oh yes, this is just the derivative of the thing up here. Yes. Yeah, that's so. Yes, absolutely, because this is delta S. So I have here delta S due to a fluctuation, and then I just I take the S, the alpha I. Thank you for because if you have the question, then everybody else has the question at least twice as badly. Okay, good. So this is the assumption of linearity, and it is the basis for a whole field of studying transport phenomena, namely transport phenomena for systems not too far out of equilibrium. But you have to realize that there are situations where linearity breaks down quite quickly or even immediately. Like if you're at the critical point, don't expect that all these expansions are going to be of much value, because then the whole assumption of analyticity of the entropy is not such a great idea. But I will not be touching on that. Now, I'm not sure. Until when do we go? Okay. So then what I will do is actually to state what is going to happen next, and I'll tell you something about Onsager, because that's always a good way to end. So what Onsager showed, and what I will hopefully make plausible in the next lecture, is that there is a relation between these cross coefficients, and the relation, this is the Onsager relations. It says that Lij equals Lji. And this is a highly non-trivial statement. It basically says that the particle flux due to the temperature gradient, if you express it in the correct way, I mean you have to have the correct expression for the gradients and their conjugate fluxes, otherwise it doesn't work, is equal to the reverse, so that is the heat current due to a concentration gradient. So this is a highly non-trivial statement. Sub-statements of that had already been developed in the 19th century, but Onsager generalized it. I will show tomorrow how he got there, but to conclude, I said I would say something about Onsager, which has nothing to do with the topic of the talk, but it's very instructive. Hopefully. Okay, so this is what I was just saying, and then I said that Onsager showed the symmetry of the coefficients. But what I will be focusing on in the last few minutes is something else. This. Because with this audience, I mean, you may not know this, but this thing is called a cigarette. And in the past, people used to smoke cigarettes, and if you smoke enough cigarettes, then what happens is the following. You see, this is Onsager's grave in Yale. What? What? It's not. It's not on. I know. It's almost his grave because his wife was buried there too. I mean, so later on, so they kept space for his wife, and so later, actually about 15 years later, his wife was buried in the same grave. I said, there she is. But there's something else they did. They added etc. Now, there are not that many gravestones that have etc. on it, and so the question that I would like to answer in the last few minutes, is why there's an asterisk and an etc. on Onsager's grave. And I mean, as it's an unusual gravestone, but actually there are other scientists who have a more conventional gravestone. And one of the examples is John Kirkwood, who played a key role in the development of entropic phase transitions I will not discuss. And Kirkwood's grave looked like this. And I don't know how to describe it. I would say it is like a job application in afterlife, something. So now the reason why Onsager's family saw it fit to add the etc. to the gravestone in Onsager to say Nobel laureate etc. is just because the two stones are next to each other. Okay, and I think that that's enough for today. Thank you.